Uh, excited to be joined by my good friend Brian S. Uh, and thanks for the sacrifice of joining another terrorist watch list with me, buddy.
Oh, you are absolutely welcome, my friend. Who needs to fly anywhere? I just learned the
Right,
love of driving, so we're okay.
right. Um, yeah. This is for educational purposes only. This is to explain the science behind the nuclear bomb, which is an incredible technology that was developed in a time where it probably shouldn't have been, given what was going on at the time. Um, and yes, uh, I thought there was no better time. So no better time. So again, this is just for educational purposes. Um, we are doctors, nuke doctors. No. Brian knows the chemistry side of it or the nuclear side of it. I know the physics side of it, so we make a really good pair. You could call us the, Dr. Oppenheimer and who do you want to be?
Uncle Touch Me Funny.
Oppenheimer and Touch Me Funny. Yes. Both notable historical figures. So,
Sorry.
we're gonna go from this lovely little uranium ore to all the way through to a bomb. So enjoy, buckle up, and
not literally, figuratively.
not literally, figuratively. Yes, we're using props.
Do not ever try to enrich uranium.
Don't ever try and build a bomb because you'll never get plutonium, and that makes me very sad.
He almost just made me spit my drink. I felt like today would be a great night for a drink. I had my wife go out and pick me up some sake because who doesn't love talking about Japanese drinks when you're talking about nukes?
Right. Yeah, I said that was wildly appropriate, and I support his decision 110%. Like, there is no better time to talk about it than drinking a traditional Japanese beverage. I don't know why that's appropriate, but I'm told it is.
I don't know. I feel like the second one made it taste better.
So, with that being said, the only people to drop a nuclear bomb on somebody was the United States. And that nuclear bomb was dropped on Hiroshima and Nagasaki. That was the fat man and the little boy. So, we'll learn both of those types. So, a traditional, the little boy nuclear weapon that uses traditional explosives, and different kind of cores, and then we'll also learn the gun type or the thermonuclear warheads that are in most of our arsenals today. So, Jacob Castro over on Rumble, if you're not on a no-fly list by now, you're doing something wrong. Well, I'm doing everything right then. So, I figured we'd start with
librarians.
Who's talking about librarians?
Jacob Castro. They found me. Somehow they found me. The librarians.
Oh. Are you sure he doesn't mean the Libyans?
Nope.
All right, then. So we'll say hello to everybody. We'll get right into it. Jason J, what's up, buddy? Man bun? It will be good. I promise. I didn't do it. He didn't do it. Great time. What's up, Xcomer? Hey, Linda. Here for edumacations. Good, because that's all we're doing here. Jacob Castro, what's up, buddy? Yes, the Atomic Duo. I'm definitely Batman. He's Robin. He's more of the gay Twinkie one. So.
I like to wear my underwear on the outside.
See? Mystic, hello. No, he definitely said Libyans. What's up, Snafu? Oh, was that one of those ones where I wasn't supposed to point out the correct answer?
Correct.
Oh, damn. I always get those wrong. Always get those wrong. Um, so welcome to my TED Talk, which would never get picked up by a TED Talk because I can't talk like that. Because I would ingest plutonium, if that in Minecraft, because I think they have plutonium in Minecraft now, don't they?
In modded Minecraft.
What's up, Fast Group? So uranium mining. So we mine a ton of uranium out of the United States. Our uranium signatures are traceable. So if there was another nuclear device that was built, they would at least know where the plutonium came from. No outcast for this. So this is the next best thing. What's up, Aaron? So these are all the sites and our production values as of recently. There's a lot of those in that upper kind of Midwest, the North Dakotas, Wyomings, that kind of Utahs, and that's actually traceable from the next point. So this is actual. Actually, let me blow myself up. I mean, bad choice of words. Let me make myself bigger. So this is actual legitimate hot radioactive ore. It is uranium ore from United Nuclear. It is radioactive. I will not lick it, Bobby. And yes, I have gloves because I don't like playing with uranium. But so this is how it comes out of the ground. It is very rocky, as you can see. Totally not real enriched uranium. It's definitely not enriched. As you'll see, the enrichment process is a pain in the ass.
Yeah.
And it takes a lot of material to enrich uranium to a weapons grade point. So
almost not worth it.
It's almost not worth it unless you're a major government, because you have to do it on such a magnificent scale. But it's really not discernible from normal rock for the most part. I mean, it is a hot sample, so there is actually radioactivity coming from uranium, but it looks just like any other rock. So,
what up, D's?
What's up, D's? Oh shit! There's a Russian here. We got to kill the stream, guys. I'm sorry.
Just kidding. He's not doing that.
No, not gonna do that. But I was thinking about it.
That's a nice scintillation vial, though.
Yeah. This is for research use only. See that? That's it right there, for research use only. So not me to play with. Damn, definitely not. Broke the rules. If I get it too close to the mic, it will make my mic go all wonky. Sometimes my camera, depending, because it's really hot.
Oh, that stuff is super, super hot.
Super hot. I actually can't talk on my phone if it's on my desk, because it's that ridiculous. So this is kind of just, again, this is a breakdown of where we're acquiring this ore from. So, you're only legally allowed, and this is not an advice channel, but you're only legally allowed a specific amount, and if you have any more than that, you have to file with the NRC, and then it becomes a problem. So
huge problem.
Big problem.
There's no other use for it, so huge problem.
Well,
not okay.
Define no other use. There's that's peaceful purposes.
Yeah, but it's not legal for a regular person to have or use.
Well, I'm not a regular person, Bri.
I guess that's right. You're meat, so you're not people.
I am not people. I am a ball of meat. I can do whatever I want. But anyways, So, how do we get from this to something that makes some kind of difference? I forget the isotope on ore. Do you know it offhand?
Um, for the ore, so we have like I think it's like 253 or something like that for the base.
Oh, I think
Um,
it's 235 and 238 is weapons grade, right?
no, 235 is weapon grade.
Oh, okay.
So
Is
236.
uranium ore. Well, you're concentrating it, so.
So 236 is a non-fissile or fissile.
So there's three naturally occurring radioisotopes of uranium, 238, the heaviest and most abundant. So this is probably likely mostly 238. There are some hot samples in this though, so there might be a little bit of 235 and 234 naturally occurring in the sample, but not enough to really make a difference. So, well, I'm using Iranian money, so I'm good. Yeah, let me know how that works out for you, bud. So how does this get from nuclear bomb? Because I'm holding this, I can shake it, I can, do whatever with it, and it doesn't do anything. Um, it, I mean, like I said, I would not ingest it or hang out with it next to you for a really long time. But other than that, it's not going to spontaneously combust and cause a mushroom cloud over my house, which my wife is very happy about. I guarantee. So once we get to that, we take it and we chemically remove all of the impurities. We take all the rocks out of it, all that kind of stuff, and we get a metallic form of uranium. Despite popular culture telling us that it does, uranium does not glow green in any way. We're gonna get to that, Comer. So, the most common types are enriched U-235 or uranium-235 and plutonium-239. So what we do after that is we do exactly what Comer says. We put it in this big long tube and we spin it around in a centrifuge and we separate out the impurities and we make an enriched sample. So highly compacted 238. It gets rid of all the rest and kind of concentrates the metal form down. Did you want to add anything from your chemical point? Because this is probably more you than me.
I'm just wondering, I wonder if they use some kind of solvent in order to dissolve the stuff that's around the uranium itself in order to compress it down, because it would be kind of hard to get, because it's not dust, obviously. So
Right.
they have to use some kind of solvent to break down the stuff around it, and then as they spin it out, you end up with like a pellet at the bottom, and as long you
Correct.
just take off the stuff on the top, add more in, or do whatever you want to do, clean it up, and call it a day. But
Right.
trying to get
Oh,
as much of it is very, very hard because this stuff's not usually. It's there's a lot of impurity which you have to get rid of.
exactly. So, I answered my own question without even having to look up another source because I already brought it up in the paper I was reading. Uranium is mined. It consists of 99.3% of U-238 or uranium-238, 7% of uranium-235, and 0.1% of U-234. Different types of uranium isotopes. They contain 92 protons in the center of the nucleus because its base number is U92, right? Or is it higher base number than that? What's the table, the periodic number for
It's
uranium?
92.
That's what I thought. Okay. In the atom center, uh, number of protons in the nucleus is what makes it uranium. U-238 atoms contain 146 neutrons, and U-235 contains 143. So the total number of protons plus neutron gives the atomic mass, blah, blah, blah. So now that we got that out of the way in the paper that I brought up to talk about it, now we can get to the other part that I brought up the paper to talk about. Nuclear fuel in a reactor has to have a high concentration of U-235. U-235 is concentrated or enriched in fissionable and lightweight reactors. The most common reactor design during fission, blah, blah, blah. We don't need to get to that because we're not doing peaceful power. So, commercially used U-235 isotope is enriched to 3 to 5%. Natural state of 7% or 0.7%. So you're enriching it quite a bit, but it's still not pure. Like we're not even close to pure. As a conversion plant, uranium oxide. So they grind it up, make it an oxide, and then they convert it to uranium hexafluoride. So UF6 to a usable enrichment facility. UF6 is used for a couple of reasons. The element fluorine is the only natural occurring isotope, which is a benefit during the enrichment process. So fluorine is nasty shit.
Yeah, I don't mess with that. It's highly reactive, especially if it's like paired up with, hydrogen, as in hydrogen fluoride, easily one of the most strongest acids I've ever heard of.
Yeah.
Will melt through the damn floor.
Yep. It's not fun. So
I don't mess with it.
Yeah. Fluoride, and they put that in your water, allegedly. So that's cute. Gaseous diffusion. So we have 3 different types of enrichment process. So we have gaseous diffusion, gas centrifuge, and laser separation. There's obviously drawbacks and benefits to all of them. So gaseous was the first commercial process used in the United States to enrich uranium. These facilities utilized massive amounts of electricity. As the centrifuge technology matured, the existing gaseous diffusion plants became obsolete. Worldwide, they've all been replaced by second-gen tech, which requires far less electrical power to produce the amounts of separated uranium. They're now obsolete. So again, this is in gaseous diffusion. Uranium hexafluoride gas is fed into the plant's pipelines, where it's pumped through special filters called barriers or porous membranes. The holes in the barriers are so small that there were barely enough room for the UF6 gas molecules to pass through, as shown in this diagram. So they're cutting it down to a very small, very fine powder, which is fantastic to breathe in, I'm sure.
It's probably fine.
The isotope enrichment occurred because the UF gas molecules diffuse faster through the barriers than the heavy UF6 gas molecules containing U-238. So the 234 and the 235 go through the membrane easier than the U-238. So the barriers are separating it out and collecting the material. So
Right.
took many.
Neutrons are so much larger than protons that just having the extra one neutron, it will prevent it from passing through the barrier fast enough. But you will be getting some 234 through there because it is smaller than 235. But 234 isn't as abundant as 235, so you're not going to be messing up your ratios too bad.
Right, and it's not going to be as detrimental to the process as 238 is,
which is everywhere. That is the most abundant.
Right. So one barrier wasn't enough, though. It took hundreds of barriers, one after the other, before the UF6 gases contained enough U-235 to be used in nuclear fuel. At the end of the process, the UF gas withdrawn from the pipes is then condensed back into a liquid and then poured into containers. The UF6 was allowed to cool and solidify before it was transported to fuel fab facilities. The diagram to the right illustrates gas diffusion enrichment. So it's really pretty simple. you're just passing it through membranes and sorting out molecularly the heavier elements from the lighter ones. So it's it's not it's not the craziest thing. So um it's really kind of a simple process. It just takes you got to know what you're looking for and know what kind of barriers and how many you're going to need to put in that specific area. Um so both operation and decommissioning of gaseous diffusion plant in Oak Ridge, Tennessee was regulated by DOE. So Oak Ridge, Tennessee is one of the original sites for the bomb. It was Oak Ridge, Tennessee, which was a completely cordoned off city. And then the other one was Los Alamos National Laboratory. Both facilities are in the middle of nowhere. I've been to both. I could see how they could hide it, especially during that time. Gas centrifuge is the next option. So this is when you're looking at a report of an Iranian nuclear weapon or something like this is the method which they use. This is also the method that the United States hacked and put a packet in to cause it to overheat and destroy their entire sample, allegedly. So gas centrifuge enrichment is the current process in which commercial enrichment is being performed in the United States and in most of the world, like I said. You have 6. So the same kind of gas is placed in the gas centrifuge and rotated at a high rate of speed. The rotation causes a strong centrifugal force, so the heavier gas molecules containing U-238 move towards the outside of the cylinder. The lighter gas molecules collect closer to the center. So it's just a collection and separation process, and they just repeat that, slightly depleted stream with the higher concentration is recycled back to the lower stage. Yeah, I saw that. I was just in Oak Ridge 2 years ago, and it's really quite a booming city at this point. So, not what it used to be. Neither site did they keep a lot of history either, which kind of pissed me off when I was there, to be honest. But they didn't keep a lot of history from one of the most consequential discoveries probably of our lifetime. So,
well, it's probably a good thing that they didn't, for various reasons of stolen info and stuff like that. But at the same time, I agree. It would be really cool to know more about the process of how secretive they had to be and stuff like that. But
yeah, and there are some docs out there and stuff like that. Maybe I'll do a show at some point. Lots of money there. Yeah. They have, for example, they have the original military gate, the white gate with the guardhouse. But it's so beat to shit at this point, and it's obviously not being taken care of. And that's kind of just frustrating to see, because that's one of the things that certainly could have been protected and taken care of, and wouldn't have given up any operational security issues or anything like that. Also, I was down there when they had a fire in the experimental reactor. What was that, 2 years ago? Year ago? Probably a year ago. I don't know.
how did that happen?
I don't know. They didn't talk about it.
Good point.
It's government, baby.
Government.
But anyways, back to this. A gas centrifuge facility contains long lines of many rotating cylinders. These cylinders are now connected in both series and parallel formations. Centrifugal machines are now interconnected to form trains and cascades. At the final withdrawal point, the UF6 is enriched to the desired amount. It must be pretty easy to remove the fluoride from it, though.
Oh yeah, definitely. Yeah, you just have to add in a super weak a weak base.
Catalyst?
No, weak
Oh,
base.
okay.
You'll rip the strong acid right off.
Oh, okay. Huh. See, this is why I keep you around. So our third option, and probably the most costly option, is our laser separation. So laser separation is under development for possible use to enrich uranium. Uranium can be enriched by separating isotopes of uranium with frickin' lasers.
Are they are
Mo-
they space lasers of the big nose variety?
let's ask AOC because I don't know.
Don't tell me that this is about a condemnation of anti-Semitic remarks when you have a member of the Republican caucus who has talked about Jewish space lasers and
Oh, I didn't know
Apparently,
you
it was.
had that. I did not know you had that clip. Oh my
Yeah.
god.
Yes, I do.
Oh,
So I think that's as good as certain. She said it, and I believe everything
I
AOC
agree.
says.
Absolutely.
But yeah, so this is I don't know that exciting molecules of enriched uranium is the way to go, and probably why it's not used in practice at this point. But
I think we would enrich or we would excite the not uranium 235. We would probably do the 38.
oh, okay, all right,
Because if you start trying to laser the 235, you'll set it off,
yeah, yeah,
which we all know what happens when you set it off. So you're probably going to end up exciting it enough so it like breaks into a gas of 238, collect that off separately.
okay. So once you get an enriched product, you put it into pellets. What's this thing that I've been playing with right here? This is a zirconium fuel rod. So you can either use it for peaceful purposes, aka nuclear energy, or you can use it in an experimental reactor. And this is actually a real reactor rod. This is about the size of them. They're very small. They're very small pellets, and you can convert them to plutonium, and then the plutonium gets reprocessed. But you just make these very, very small pellets. You fill them with the pellets, and then you arrange these in a control rod kind of lattice with other, and these are zirconium rods. And yeah, so that's how you make your shots or your pellets to turn them into plutonium, which then becomes processed into things like a demon core, which is probably the most interesting thing I've ever seen. You've heard of the demon core, right?
No. I've heard
Seriously?
of Armored Core. That's a good video game, Armored Core 6. But no, I've not heard of a Demon Core.
I wish I had this sound clip. I'm going to type it in the back.
God, I love how you're touching all your stuff with your gloves on still.
I know, right? I'll wipe it down afterwards.
Yeah, I don't mess with really hot chemicals and stuff like that. Proceeds to touch with the gloves that he touched everything.
I I'm trying to find one that I'm probably not going to get. Well, here, I think this is important because this is well, we'll get into that later. Remind me about Demon Core later, because
Demon Core, all right.
Demon Core is incredibly interesting. So that takes us into we've used our uranium sample. Actually, I'm done with the uranium, so I should just take the fucking gloves off. But so we enrich the uranium, we put it in here, and then we expose this to a reactor. We shoot things at it, which Brian's going to talk about, and then then we get plutonium 239, which is nasty shit. So, what do you want? You want something else?
Yeah, I mean, if we want to start with what I sent you, the PHET sim,
Okay.
the fission one nucleus would probably be the best one to start with.
It's not coming up right because hang on, I'm gonna have to rearrange Windish. didn't like the way I had it. All right. Well, why is that still doesn't look right? I had it up like I actually was paying attention. Graphics initializing.
Here, you can share my screen.
Look at that.
All right. So now we have the uranium-235. This is the molecule of it. For all intents and purposes, I'm just gonna hit this button now. But you see, it busts apart, right? So underneath here, we have a graph of the potential energy that it can have. Right now, if you think about it, kind of like a volcano, that's probably the best way to think about it. Where once the lava gets enough energy to break past the ridges here, it will fall down the side, towards wherever it's trying to go to. So as you shoot it, it goes up and over, busts apart, and how far it goes down versus how far it needed to go up is how much energy it had gained when it started falling, essentially down the potential energy graph. All that energy is going to be released, which then would allow it to crash into another molecule of uranium-235, which it gives it enough energy because it only has to go up a little bit before it goes down 2 or 3 times the amount. So every time it busts apart, you get double to triple the amount of energy. I'm just using arbitrary numbers, double, triple, fine.
Mhm.
So then you can eventually go and you can start getting, let's say I have 100 nuclei. It's pure stuff. This is some good shit. As soon as you shoot one, it will bust apart and start blasting into other ones because it has enough energy in order to do so. If you didn't have enough energy, then it wouldn't continue reacting.
Teacher.
Yes, sir.
What happens in nuclear power plants, though? Why doesn't it just always burn it down?
So that's a good question. So in nuclear power plants, we generally try to control it as best as we can by absorbing some of that energy, before it's able to continue reacting with other molecules, with other uranium particles. So it doesn't start cascading, or when it does, you get an elephant's foot.
Yeah.
Because it just keeps reacting. But so say you go and fire this, because I have these control rods up, it's blocking most of that output. But if I start removing them, it will allow for more. Oh, I'm bad at this. It will allow these reactions to continue going through until I go put the control rods back up, and it will stop the reaction.
Theoretically.
Yeah.
And those are graphite control rods for the most part. So
Usually, right? I think they're trying to use other stuff, but graphite's the best. It's just a little weak at the moment. I think we might be trying to switch to graphene at some point.
It's a decent moderator. It just you need to stay on top of it or it will melt. So
Yeah.
But like Chernobyl.
But yeah,
Happens.
as soon as you get up and over, you get the cascading effect because it's enough energy to break apart more. These daughter nuclei, as they call it in this, are very, very, very high in energy.
So what do they decay into? Do you know?
Off the top of my head, no. I would assume it's half of whatever uranium is. So whatever, I think it's like 90 something, 96. So I think half of that, which would probably be, I think, what, lead?
Lead wouldn't make sense. Here, let me see.
I don't remember off the top of my head what the amount of protons, and I think it's like 96. I cannot remember what I said it was, but whatever half of that is on the periodic table.
Those are decay though. That's not what I want. I want split. Barium.
Barium.
Krypton
All right.
and barium.
There we go. Yeah, it's about half of that, I think.
Yeah, somewhere in there. So, and it depends if we're talking about fission, which is different than fusion in the starting material.
Correct.
So, one we use heavier elements and we split them apart. The other one we use lighter elements and we push them together. So, we're specifically talking about in the context of power and our original bomb design of the little boy. We're talking about splitting them. And so I think this is a good indication of a chain reaction. So uranium into krypton and barium, and then uranium, krypton, barium, krypton, barium, krypton, barium. And then it continues to break them into those daughter particles all the way down until it's interrupted. So
until there's no more left, until it misses.
Right.
As soon as it starts missing, you're screwed. There's no more reaction happening.
Right. So here you have this neutron, this little neutron that's going through and breaking it up, and we have these flying off and hitting into other ones. So it's a sustained chain reaction. That's why it's so dangerous. That's why it's
like
so
playing pool almost.
Yeah, I could see it like that. So, did you have anything more on your side, or right now?
I do just want to say that so the reason why the other isotopes of uranium, they don't work for so like 238 per se. There's not enough energy in one daughter nuclei, daughter particle, to start the chain reaction of that one going. 235 has a really small well. 238, the amount of energy to break it apart to get out of the volcano is very, very, very high. Not enough for the daughter particles to have.
Right. And so here's just some numbers on it. So energy release is 210 mega electron volts of fission, 90 quadrillion fissions per second in a 3,000 megawatt reactor. So 90 quadrillion per second. So we're talking about tons. Tons, because I mean we're still talking microscopic. I don't actually know what the size of a nucleus is, but we're talking very, very small.
So we're talking about 6.02 times 10 to the 23rd particles in 235 grams of this substance.
Wow. Okay.
So
Kyle Hill has
that's a lot of zeros.
A lot. Kyle Hill has some good videos on Demon Core. Yeah, he does. He does. He certainly does. But he would definitely strike me 100%. So okay. So I had one more. And this is all coming to a place near you. We'll get into that later too. So beta decay antineutrinos, and these are the chain reaction neutrons that are. You also have all the X-rays, beta particles, alpha particles. That's where you get your radiation from in the reaction, and the radiation spreads just as far as it can. All right, Jacob.
602 sextillion particles per 235 grams.
Wow.
So think of a kilogram of this stuff. That's a lot of energy.
That's a lot of energy. A lot of energy. I think I'm just going to stay with, well, I like this paper better. This is an actual paper. I don't know. Fuck. We'll see where we're at. So, I don't think we need to go all the way back to this. What's an electron? What's a proton? What's a neutron?
Oh boy, we're back to this again.
Oh shit. Active shooter at Texas State Fair. If anyone's around there, be careful. Yes, please do. That sucks. No, don't be sorry. Don't be sorry
Suspect
at all.
is in custody,
Suspect in custody. Good.
but everyone else, I mean, still stay safe. It's
Right.
suspect, not 100% the person who did it. So keep safe, find shelter, go home, do what you need to do.
Yep. So, yeah, here. So, here's the example. Carbon, we're not going to go into isotopes of blah, blah, blah. Alpha, beta, and spontaneous fission with gamma radiation. There's the thing we saw. So, this is the flip side of it. This is the peaceful purpose of nuclear energy and nuclear fusion. So, you just take some heavy water, some deuterium, and yeah, you make some harmless helium and a hell of a lot of energy. More energy than fission with fusion. So fission is breaking them apart, fusion is squishing them together. Rico Fermi. Nuclear fuel. Okay. So 94, that might be. Wait, what? Oh, plutonium. The thing I can't get. We should look into plutonium.
Getting it or
Yes.
no?
No, we're going to look into a profile of the element that if I could own any element in the world, it'd be plutonium. Yes. Radioactive, a profile of the element plutonium. I hope that's not real plutonium, because that would be pretty terrible.
Those look like bracelet squares you'll get from like Hobby Lobby, to be honest. Like
That's that's what I'm saying. If that's actual plutonium, one, nobody should have went through the process of making that, and two, some kid's gonna mistake that.
right, they're gonna eat it.
Yep.
It's gonna turn into a house episode.
Oh no.
What happened? He ate plutonium. Well, he's gonna turn into a horse.
Yep. So, plutonium first identified in the 1940s. Plutonium has been used for both creative and destructive purposes. The late physicist John Coffin once called plutonium the element of the Lord of Hell.
Makes a lot of sense.
Plutonium is nasty, and I joke about getting plutonium, but one, nobody's ever going to actually give me plutonium. Thank God. And two, I don't know that I want plutonium ever.
I wouldn't get within a 10 yard radius of that shit. Nope, not gonna happen.
No, and it has to be heavily regarded and taken care of, and yeah, it's not the greatest idea.
You put that stuff in like a can of water, sure, it like some of that radiation might get blocked, but it'll boil the water so damn fast.
Yeah, plutonium's not anything to fuck with. But every atom of plutonium contains 94 protons. By contrast, there are only 92 protons per uranium atom and 93 in each neptunium atom.
Can we get that one? Neptunium?
I actually don't know. I've never tried to buy neptunium.
I'm going
to right now. I think it's I don't even think it's fizzle.
It's not. It's definitely not. It's an odd number. It's the even numbers that are fizzle.
Yeah, you can buy it for a 50 millimeter cube for $700.
Yo, you want to send me one?
Bro, I was just gonna ask fucking Comer to send me one. Oh, you can buy a smaller cube.
That's a big cube.
It is radioactive.
Slightly. It's probably not as bad, but yeah, it definitely would be. I think isn't it a 13? Isn't it like a line 13?
Yeah. I mean, it would be, because it's between plutonium and uranium. Right? I don't want to buy neptunium from Etsy. I don't think that's going to be a good source.
Why? Who's selling it on Etsy?
I don't know. Oh, apparently they sell all kinds of element cubes. Because here's some cesium. Not the good kind of cesium, but because you have reactive cesium and base cesium. Damn, I might be into something here. Shit. Americium. I already have americium. Indium. Thallium. Mendelevium. 101. Alright, I'll stop shopping for a minute.
Yep, do
I
that.
have,
Yep.
I have some ytterbium. But that's cheap. Anyways, since the two elements were named after ancient gods and planets, Uranus and Neptune, plutonium got the same treatment. Discovered in late 1940. Plutonium can only be made in. It's not a naturally occurring element. It's something that we've had to produce. So, it has a way too active decay cycle, half-life. Shit. So it wouldn't be there. Like, we wouldn't find it unless we make it.
Which is really good for us, by the way. That's probably why we're fine.
No.
If that stuff was able to be naturally occurring, we would be so fucked.
Oh shit, that's your Etsy account?
No, send me some then. If that's yours, give me some.
I will put my fucking address in chat if you send me some.
He's already put my address in chat. Send me some.
Plutonium is used for military purposes. Is recovered from uranium fuel that's been irradiated for 2 to 3 months in plutonium production reactor.
Oh wow.
Yeah, it takes a long time. So you're uranium-235, and you are irradiating it for a very long time. It takes about 22 pounds, 10 kilograms to produce a nearly pure plutonium-239 isotope to make a bomb. That type of bomb requires 30 megawatt years of nuclear reactor operation with constant fuel changes and reprocessing the hot fuel. That's why it's really expensive too, because you have to continue the heat cycle on the fuel. Like it has to get hot enough, irradiated long enough, and for an extended period of time that's uninterruptible to be able to make it. They actually make that at Oak Ridge. I wasn't shitting about it. Right there, Etsy.
$53. That's awesome. Wait, no, that's not right. That's not actually. That's
what I said. That's what I actually said.
Glass or something.
Well, yeah, it's a cube. Yeah.
Radioactive symbol, no sample. Fucking.
That's what I said. Yeah.
That's dumb.
The other ones did have samples, the other elements, but you can buy neptunium. It's just really fucking expensive and has no actual process for making anything as useful.
Paperweight. Radioactive paperweight.
Sure. What do you think this thing is? So that's where we're at. Plutonium stockpile. Currently, the United States has about 96.6 tons of plutonium and a storage problem. Much of it's currently stored in a building where the Savannah River site in South Carolina. Hey, Bri.
Yeah.
What are you doing this weekend?
Probably watching anime.
You want to go for a drive?
No.
So today, more than 1/3 of the energy produced at nuclear power plants comes from plutonium because it's highly radioactive. It's intensive to make, but it's highly radioactive. So, and it produces a lot more of that reaction. So
it works really well for what it does.
Yes, it does. It but it is incredibly toxic.
Yeah.
It's not only radioactive, but it's also toxic. So plutonium is radioactive, though you'll likely never be exposed to it. Robert Hazen at Carnegie Institution for Science says there are no natural sources of plutonium. It has to be made through breeder reactors, so all plutonium used on Earth is human-made. And that's another one of those where we can tell the signature of where it was made based on the plutonium itself. So we know where the plutonium is made because there's not enough of it out there. So we can tell if it's made from, Oak Ridge or Savannah River or Maharashtra or Deeze's house or, pick your choice. It can be released to an environment via industrial plant or from container. However, the levels in plutonium in the air, water, and soil are extremely low. However, if you are exposed, it would likely be breathing in radiated aerosols or skin contact. And many factors will determine whether exposure will harm you. Basically, any fucking level of plutonium will harm you.
Yeah.
Yeah, you would certainly die from toxicity long before the radiation. So, when you breathe it in, some plutonium will get trapped in your lungs and move to your bones and liver. It actually calcifies in your bones. It's pretty disgusting. If you swallow it via food, a trace amount can also spread to your bones and liver. If you touch plutonium, very little, if any, will enter your body, but it can burn the skin that came into contact with it. So, while it's a radioactive element, plutonium is far from being the most toxic substance known to man, as Ralph Nader once proclaimed. It's pretty toxic. I wouldn't be playing with it. I'd be using gloves effectively if that was plutonium instead of uranium. I can handle big boy materials.
I wouldn't mess with it. I would say I'm not working here. Sorry, dude.
Speaking of not working here, so this is the early development of the bomb program. This is the Demon Core in 1945. Yes, you can see that this is a true depiction, although not accurate to everything, but this is a true depiction. They were using screwdrivers and shielding bricks.
Heads?
They are. So we'll watch a short clip, and you can see what happened with the Demon Core.
Everybody ready?
Meter's ready.
Here we go.
Those guys are never having children.
Got it? 40. Everybody back right now. Behind the wall.
Thank God for early scientists. What would we be without them?
Uh-oh.
Nobody move! Don't anybody move! Damn it! Take out
That would have been-
metal. Drop it to the floor. Mark the position you're standing in. Get out.
That would have been incredibly hot to the touch.
That would have been so hot. What are they doing? Trying to see how much radiation they got or something?
Everybody should make it,
If they got a lethal dose, yes.
except me.
And they actually fucked up a second time and knocked over the shielding blocks, doing almost the same thing. So, it's called Demon Core. It was there's plenty of different stuff on it. I might do a show on it at some point specifically, but
This one dude got the lethal dose or whatever, and the rest of them were fine or something. Is that like the story?
I think
Or did he
I'm
live?
not sure. He didn't live. I know he didn't live. I don't know the status. I don't remember right offhand the status of it. I'll do a show on it at some point. But yeah, they very shoddy work. I mean, that one of the most dangerous substances known to man at the time, and they're just playing with it and a little. I mean, that's relatively accurate. So, yeah, yes. And it happens incredibly quickly. So that's the Demon Core. It's kind of interesting. So, are we ready?
Absolutely.
Okay. So, I like different parts of different things. So so let's start. We'll start with the implosion designed nuclear weapon. So this is the little boy. This is the original bomb dropped on Japan. So this is a traditional fission nuclear warhead. And so this is kind of what it looks like. So they learned from the Demon Core and actually printed some pieces so you could actually see kind of a cross section in 3D space. So they learned a little bit. So they put a damper. So this is a damper shell. And in the damper shell, there was some space from the plutonium core. So instead of having it where it was incredibly dangerous, like in that video, made just a touch of space and filled that with a non-reactive fluid. Here's also a damper, so it could basically implode the sample and cause it to go critical in a much easier way. So this would be your plutonium core. This would be your damper. And then we have this, which would be your explosive. So you'd have your explosive lens. So it'd be in a hexagonal pattern, because the important part of this is that everything had to fire at the exact right time to compress this ball equally on all sides so that this mass went critical. If not, your weapon failed. So you had to make sure that you had the correct geometry to be able to apply pressure equally around the entire ball. So we have a cross section of the explosive lens. Core goes in explosive lens. This is a combination of high and low explosives arranged. It would blow up, and it would blow up as a spear, and it would compress this until this went critical, meaning it would introduce the neutrons from this outside shell to start breaking apart that internals. This is kind of what your explosive lens looks like. One of the biggest challenges with this is each of these hex patterns had a specific kind of detonator. The detonators had to be timed. I forget what it is. I think it's in this paper, but it had to be timed to a degree that was pretty impressive for that time period, because we didn't have computerized systems and stuff like that to be able to do it. But this is what one of these hexes would look like from the hexagonal outer core of the bomb. And it would be like this, and you would have a high explosive on the outside, you'd have low explosives filling in the gaps on the inside, and they would work in tandem to apply equal pressure all the way around that core to make it go supercritical. That was always the design and the idea behind that.
So when you say high and low, do you mean like fast and slow explosives?
Yeah, pretty much. And I'll get a little bit more into that. So
Sure.
So this is their figure. So same thing that I have. This is just in 2D space, whereas that one's 3D. So your tamper, it can be iron, it can be uranium. It can be a bunch of different things. This specific one has a reflector, so it has a uranium reflector that would aid in both the compression and turn the neutrons back into the plutonium. This one has a polonium and beryllium initiator in the middle of the core. Some of them didn't, some of them did. There was a wider range of different tests to begin with. So the outside, this is that tamper, so this is that outer shell. And this specific one, about 200 kilograms of iron. So it would be pure iron. It would be just there to help compress and to kind of slow things down a little bit. So it was just there to help that lens just make more criticality towards the center of that. And then once we get out there, we have firing set, iron energy source, timer switches. You have your 32 detonators placed in equal part. Your high explosive, 250 to 500 kilograms of high explosive like RDX. What? Oh, it's the other page. And then here it is. So wiring system that sends electrical impulses, detonating device used to ignite high explosives. High explosives shaped charges made from materials such as HMX, RDX, and TATB. All very fast explosives. Tamper a dense material such as natural uranium that holds the core together by inertia. So that was really in the bigger core bombs, it was to hold everything together so it didn't just you didn't want there to ever be a space for that plutonium core to just shoot out, because then you wouldn't have a reaction. You'd have some radiation, but you wouldn't have a reaction.
Ooh, pretty flower.
Yeah, pretty damn destructive flower.
Flower turns into a mushroom.
So, and again, the reflector can be something like uranium. They really experimented with a bunch of different things, but this one says beryllium. So you're bouncing neutrons back to the center. So you want everything in the core to stay in the core, because explosives, the RDX isn't going to stick around for very long, and it's not going to build a barrier. So that's what the levels are, to keep those neutrons interacting and breaking apart, as we talked about earlier, those atomic nucleus to release that energy and cause a chain reaction. Now, the smaller you can get that center core, the closer you get to criticality, and the better chance you have of complete detonation of all the materials inside of it. Now, on some of the newer bombs that are limited, you have different materials outside that can be exchanged or changed so that there isn't as much criticality in the middle of the bomb. So the so-called implosion weapon, which is the most common design used today, the weapon is armed with detonators that initiate the explosion regardless of the way the weapon is delivered. A missile, bomb, artillery shell. The detonators fire simultaneously to set off a charge of high explosives that ring the outer surface of the tamper. These high explosives, I can't say X's tonight, I don't get it, are finally machined in a lens configuration that sends shock waves into the center of the weapon. The shock waves compress the fissile core of uranium or plutonium into what's known as a supercritical state. So that's what we just talked about and kind of demonstrated. So, here's a little bit more about it. Each fission event releases a large amount of energy from light, heat, and radiation, so successive generations of fission events in a chain reaction will produce exponentially increasing amounts of energy. The key is to create and sustain a chain reaction long enough to produce the desired explosive energy before the fissile core rips itself apart due to the intense pressure created for energy release. For example, 99.9% of the energy released in a 100 kiloton bomb, 1 kiloton is 1,000 tons of TNT, nuclear explosion is released in the last 7 generations out of the total of over 50 generations and occurs approximately 0.07 microseconds. So you're waving and you're continuously compressing. So you're continuously sending waves of energy into this core to compress this core more, little by little, till criticality. And the idea behind it is you wait, and that's the design of this explosive lens. So you want to wait until you have enough pressure built up that you know for sure you're going to get that criticality. So you want the waves to keep pounding it. Think of it as if this plutonium core was a hammer, or it was go roll up some tinfoil, grab a hammer, and keep trying to smash this core smaller and smaller. Your blows with your hammer would be semi-equivalent to what's going on. It's just a matter of time before bad people get one. Yes, it is. It is. The purpose of the tamper is to hold the core together long enough for necessary fusion generation to occur. So sometimes it's designed, other times, especially in the early program, you either got much more than you originally set out to get as far as fission's concerned, or you got much less because of the materials used in the reaction. Because that can really make a difference in what kind of yield you're getting. So
If it's not pure enough, you will stifle the reaction. That was a
Right.
big problem we had in the beginning.
Yep, for sure. So this is the second. This is what they classify as, and I don't like this picture, so I'm gonna go just for the picture. So this is
Much
what,
better.
yeah. And this gives you kind of a cross section of the explosion of the core. So you're generating waves with that high explosive lens, and you're compressing that plutonium core. So this other type is called the gun assembly method. Often they'll use a implosion assembly method with a very successful damper as a shield. So they'll actually take this first section, they'll place a shield around it to try and direct it down. And you're using a plutonium core device, but you're literally shooting it into the subcritical pieces of 235 in the uranium core, making it thermonuclear, and you put all kinds of things like hydrogen and wonderful things in there. So this is the bottom of the gun piece. So you're going to have same basic thing. You're going to have some kind of uranium, or based on what your bomb design is going to be. Then you're going to have this main core. This is the core that you're trying to trap this radiation in for sustained chain explosions. And then you're going to have like a density foam, which is what most of them ended up being, of different isotopes of different elements like deuterium. The foam goes in and it isolates and does a couple jobs. One, it holds up this rod, and again, this is a cross section. if I can put it back in. It holds up this rod, and it would fill this whole cavity. So you'd have the uranium outer shell, you'd have whatever fissile material you use for the rod, and then you fill it with this foam that would induce chain reaction. So you're literally, what you're doing is, essentially, and not because you want criticality or you would use something different. What the hell, Stevie? What's up, buddy?
Hey,
Good to see
Steve.
you, man. We're talking about building nuclear bombs.
Cookies.
Nuclear cookies. Good to see you, buddy. So what we're doing is you're taking a shot with this. I don't know why they never tried to make one like this where you just literally shot it out, but I guess you're wasting fissile material. So they take a gun like this and they're literally dropping it. That was almost good. They're literally dropping it into this and making that core react with the foam to make more chain reactions. So make more shit. I didn't bring myself up big. So you're bringing that and you're shooting that ball. We just use this. So essentially you're putting a big dome on the top of it so it will compact and it will go in the direction you want it to. You're shooting this ball into this rod so you can compress this and cause further chain reactions to go throughout this whole process. And that's when you get to your big bad thermonuclear bombs. So, and that is the gun type, and that's what's going on here. This one doesn't have a uranium explosive. It's just a shield or a lens that concentrates the chemical conventional explosive into the fissile material. So we'll go back to this because I think it is better stuff, but I didn't like the picture. Explosive, so legend for figure 2.1. Explosive propellant, chemical explosive, analogous, and I can't say that word, analogous to, but not the same as high explosive in an explosion design. So again, it's very similar, but sometimes they just use plain explosives, just high explosives. But tamper, not shown in the diagram, but used for the same purpose, and composes the same material as in an implosion design. So again, we're using the same core. We're using the same high impact lens. We're taking the core, we're smushing it down and trying to get critical here so we can carry critical into like a gun, like shooting a gun down the... There is at least one FBI informant here, Andrew.
And it's definitely me.
We also have a Russian. Like, we have all our bases covered.
I cover two of them. FBI / black, so we Gucci.
Yeah. So, subcritical mass and supercritical mass exclusively for U-235. For this design, plutonium-239 will not work. So plutonium tends to like to blow shit up.
It will premature. It will pre all over everywhere.
Oh, it's gonna come and all over everything.
Well, I'm gonna come.
So, that's why they separated the gun and the thermonuclear, but they're pretty much the same thing. So we'll just go down to thermo, because that's why I was like, why are they not using uranium core in that explosion? So that's kind of the middle.
Slam two shit together, call it day. Thermonuclear is more fun.
Well, a thermonuclear is a gun type device, so they're very similar. And I was just explaining. Thought the show was Rumble only to fuck. No, I'm perfectly fine with educational. Welcome to my TED Talk.
Yeah, I mean, I think everyone should know how they got dusted.
I agree.
They came all over the place.
Where did my do not come? There we go.
Come.
Aw, Kamala, please.
All right, so this is what I was explaining. I didn't know the gun devices are not. They're not real, boys and girls. They're just not real. Fuck this paper. Anyways, they don't use them. I've never seen them practically used.
They
I
have
know
not been.
we have researched several different types, but gun went to thermonuclear, and I just didn't know they would delineate between the two, but whatever. Primary stage fission implosion device as described in section 1, typically boosted with deuterium or tritium gas. Deuterium is fuck, I forgot.
So it's hydrogen with an extra fucking new shit.
H2O2,
Neutron.
right?
No. Deuterium is specifically the hydrogen. So it's basically heavy hydrogen. Deuterated water is that, and then H2O2
Okay.
is hydrogen peroxide.
Yes. Okay. Yeah, you're right. So it is a specific type of hydrogen. Tritium is H3, right?
Tritium, is your H3.
Okay. Spicy water, heavy water.
Well,
Heavy water
deuterium is technically H3, but you add another thing on there, then you got. Wait, H2 is deuterium, tritium is H3. Yes, correct. Sorry.
Right. That's what I said. No, you're good.
Yeah, 100%.
Okay. So second stage, so this is the primary stage. It's the same thing we went over in the first stage. And the little boy, this is what I thought we were talking about earlier. So, my problem. The second stage is this fuel composed of lithium deuteride. So here's your cylindrical rod of 235 or plutonium 239. Here is your lithium deuteride or other specific. Usually they're foam. They're foam for impact resistance and foam for the properties it causes to slow it down, and sustain a thermonuclear explosion. And is surrounded by casing of uranium metal. Fusion
Not
reaction
235, 238, the non-reactive shit.
correct. Yes.
Still hard as hell. Like
Deuterated water
hard.
is sweet. It tastes pretty good too. Have you ever drank it?
I have not gotten a chance to. I want to though. I wouldn't drink a whole lot though.
No, I would. I mean, it's not technically harmful. It's
a little bit.
It's funny tasting. It's not like if you. Well, there's deuterium in standard water. At I forget what the part distribution is, but
actually, aspartame would probably be better for you than deuterated water. Deuterated water sits in the kidneys funny. It's a little heavy.
Well, it's slightly heavy. Deuterium is a stable isotope of hydrogen, mass number of 2, present in natural waters in the form of HCO, at a concentration of 16.8 moles per liter, equivalent to 150 parts per million. So it's pretty. You're getting it in your water.
Oh no, you are getting some of it. You're not going to be able to get rid of all of it 100%. It's just at small amounts, it's fine. It's just if you drink too much of it, it will start to affect you in weird ways, make you dizzy, do other stuff.
I wouldn't drink this shit by the gallon, but a taste isn't bad.
No, a taste won't hurt you. A couple of drops or like a small sip ain't gonna hurt you.
Yeah.
25% causes sterilization. If you replace it, 25% of that with your body of water. So if you go and drink
oh yeah, if you're drinking
gallons,
a lot of it,
you're gonna don't drink a lot. You'll be fine.
Okay, now I feel like we have to fucking go over a gun design because. Okay, let's do this in English real quick. they shoot U-235 at U-235 with conventional explosives. So it's a dart with a rod. So everything's 235. There's a subcritical mass of 235 at the bottom, and they literally shoot using conventional explosive down a tube U-235 in a point, and it reacts with the other U-235. Obviously, terrible design.
It's
And
flint and steel versus flint and steel with gasoline.
correct.
So flint and steel would be the gun design. Flint and steel with gasoline is the thermonuclear.
Correct. Yes.
That's how I would describe it after seeing both these designs.
Yep. They're pretty similar. They're just slightly different. So
One was got the explosive.
right. The fusion reaction commonly employed is that of deuterium and tritium. The tritium is created with lithium, and lithium deuteride reacts with a neutron. So it's neutron dense so that they can fly more neutrons around. So spelling is aspartame. Aspartame? I don't know how to spell aspartame. So a thermonuclear weapons employs fusion as well as fission. Fission is bringing together. Fusion is pulling apart. Helium-4 and a neutron, blah, 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 blah. So 239 plutonium and 235 uranium have been used in nuclear explosives in fission weapons. Approximately 90% of the effort went into making America's first bombs was devoted to producing these two materials, which is no easy task. And why they won't give me plutonium. So there's more about plutonium. So this is some fun facts about plutonium. Plutonium needed to make a weapon 4 kilograms, weight of a solid sphere of plutonium just large enough to achieve critical mass with a beryllium reflector. Diameter of such a sphere is 2.86 inches, so very small. This is probably 2.86 inches. Where did my ball go? Anyways, I don't know where the hell it went.
That was probably pretty damn close. That looked almost 3 inches.
Yeah, probably pretty close. I don't know where it went, but
I'm really good at measuring 3 inches.
well, you just have to look down. I certainly appreciate this black science guy. Oh my god. 4.4 kilos, the amount of each, or estimated amount used in Israel's fission bombs. Wow, that was interesting to throw in there.
Yeah, that's about the size of Gaza. You know, that's enough to take. Sorry.
5 kilograms estimated amount needed to manufacture first generation fission bomb today. 6.1 kilograms used in the Trinity test in 1945, and the bomb dropped in Nagasaki.
Oh, so there we go. About a third of the size of Gaza.
Yeah.
Or 2/3 size. My bad.
15 kilograms weight of a solid sphere of plutonium just large enough to achieve critical mass without a reflector. And that's why there's a delineation between the different bomb types and the different setups, because some of them, if it's large enough to achieve criticality on itself, then you don't need the reflector. If it's not, then you need something to keep those neutrons in and continue the chain reaction of the process. Plutonium generated by various reactors, 5.5 to 8 kilograms per year. North Korea's 30 megawatt thermal Yongbyon reactor moderated by graphite. That's the one they just shut down to collect the fissile material to build a bomb.
Oh, good.
Yeah. 9 kilograms per year. India's 40 megawatt thermal Cirrus reactor moderated by heavy water or deuterium.
Deuterated water. Deuterium's the hydrogen.
Deuterated water. Heavy water. We'll just say heavy water.
Heavy water.
12 kilograms per year. Pakistan's 50 megawatt thermal Kushab reactor moderated by heavy water. Oh, that's the one that the U.S. just blew up. I mean, I'm sorry, that blew up all totally on its own, and it didn't actually blow up. It was just a fighter jet going over that broke the sound barrier. We were just all very
buy
confused.
more gasoline, I guess.
25 kilograms per year. India's 100 megawatt thermal derive reactor moderated by heavy water. 40 kilograms per year. Israel's more than 100 megawatt thermal Dimona reactor, also moderated by heavy water. And 230 kilograms per year. Iran's 1,000 megawatt electric Bushehr reactor supplied by Russia and moderated by ordinary water, not yet in operation. DeGrasse? Yeah. Terrible guy.
Yeah, absolutely.
If you know anything about history, heavy water was a huge cause for concern in Hitler's attempt to develop a nuclear weapon, so much that he took over, what was it, Norway? That he took over the...
I'll be honest, I have no idea about him.
Oh, okay.
I didn't follow up on that, anything like that.
Gotcha. I know he took over a specific country just so he could get their deuterated water or heavy water.
What?
And where are we at? More than 36 metric tons. Israel's more than 100 megawatt thermal Dimona reactor. And 76 metric tons. India's 100 megawatt Derva reactor. Before being used in a bomb, plutonium must be separated from the intensely hot and highly radioactive fuel rods from which it was created in a reactor. Fuel rods like this.
Yeah, those are the
Plutonium
things that we have
fuel rods.
trouble disposing of.
Yeah.
Which is why people are like whining and complaining about nuclear energy. Because they're like, where are we going to put them?
Where are we going to put these?
Florida's like, let's make them to roads, I guess.
They're just zirconium. There's not much to them. They're zirconium, and
they're less radioactive than the material originally put in them, but they're still a little radioactive when spent.
I mean, this is a spent rod that.
Yeah, you put a Geiger counter up to that, it might, ring a little bit. Not much, but a little.
It doesn't much.
But enough for people to whine and complain about. You go into your basement, it will probably ring more.
Oh yeah, probably from the, what the hell is it called? I forget what it is, but what's up, Fed? Fuck you, my new video is available. All right, I'll go look at it. Norway heavy water sabotage was a series of Allied-led efforts to halt German heavy water production by a hydroelectric plant. So yes, Norway. Okay, I was right. I haven't even seen your video yet, Fed, but I will.
I don't even know who you are.
After.
Send me a link so I can figure out who the fuck you are.
Chemical extraction of plutonium before being used in a bomb. Plutonium must be. Oh, I already read that.
So this is all about the creation.
Yeah. So again, you put the pellets in this rod, and the rod goes into the reactor, gets bombarded with particles. This becomes slightly radioactive. If Bobby sent me a super chat, I would lick this, but because I'm not that worried about it.
I wouldn't be worried about that either, personally. Radon. Yep, it's radon gas. It's
radon. There you go. There you go. Some of the equipment needed to make plutonium. Oh shit! Let me take notes. A nuclear reactor. Fuck! I don't have one of those.
Not yet. You can be a Boy Scout and make one in your backyard. You heard about that guy, right? He got arrested.
Yep.
Poor guy.
Heavy water graphite. I mean, I have some graphite. A
Heavy
plant for
water's cheap-ish.
it is relatively cheap. A plant for fabricating fresh nuclear reactor fuel. Oh fuck! How many of these do I need again? 7%, 5 grams. Do the math.
Where?
How much was in it? 1.7% is 235, and a 5 gram vial.
Ish. I would just round it 1%. I mean, for easy sake. So 1/100th of that. So I mean, you're looking at 20, 240 milligrams ish. Maybe.
Yeah, I could do something with that.
Maybe.
Plant for chemically extracting plutonium from spent reactor fuel. See, I don't have one of those. Large quantities of pure reagents or Purex or other plutonium extraction processes. Remote handling equipment for irradiated fuel. Nah. Shielded casks to transport radioactive material. Nope, that's what the dumpster's for. High density lead glass radiation shielding windows. Rookie. Radiation hardened TV cameras. Why? Fuel chopping machines. We could make it happen.
I will order 7.5 milliliters of deuterium if somebody gives Mighty Meat $102.30.
$235 to make a weapon. Solid sphere of 100% of uranium-235, large enough to achieve critical mass with a beryllium reflector. So this just goes into the different things we've already been through: the centrifuge, the gaseous diffusion, the EMIS, aerodynamic processes. Right, getting your pure 235 and getting rid of that 238 that doesn't do much for you.
The pesky 238.
Critical equipment needed to enrich uranium. So, high strength aluminum, marrying steel or graphite to make centrifuge rotors. Spin, form, or flowing machines, filament winding machines. I have all that so far. Balancing machines, sintered nickel for gaseous diffusion barriers. We could come up with, nickel's cheap. High purity fluorine. Yep, I'm out. I'll play with uranium.
No.
I'm not fucking with fluorine. Special valve seals and pipelining. Pumps from moving uranium hexafluoride at high pressure. Yeah. Laser isotope separation equipment. Yeah, I'm out. So this is all the things you need. That's why it's so difficult for countries to attain nuclear weapons, because there's a ton that goes into it. A ton of different things and different processes. Secondly, you're doing it on such a large scale that it's really hard to not see it. So basically we have spy planes and different things all over the world. If you start building a plant that's worth building a nuclear device, somebody's going to find out about it pretty quick. So, ever read about the radium girls who died after working about radium dialcohol? Yeah, they would, people would paint their teeth with it. They'd paint their nails with it.
Yeah, it was not great, but it was
Right.
hard, so they liked it, but
yeah,
it's never good for them. I did actually do something a little interesting with the one slides that I was showing before. Just to show the absolute need to refine this stuff.
Yeah.
So this is what happens if you don't refine it down. This is like 50 molecules of 238 to the 230 or 25 239s. So basically, this is significantly more 235 than what Mighty has. And if you break one apart, notice how it barely reacts. It won't react. Even though there's a lot of it still, it's going to miss a lot. That's all I wanted to show, because it was like the amount of reaction we would have if you didn't refine it down would be 0. You would not destroy a city with that.
You wouldn't destroy much of anything.
Yeah.
No, you're totally fine. And one of the things is that many people have talked about dirty bombs. So you basically just take an amount of radioactive material, you blow it up with traditional chemical explosives, and it will spread that radioactive material, although not the impact, and you're not going to have the blast waves, you're not going to have the radius, you're not going to have the fireball, won't have the mushroom cloud, but the idea is that a terrorist organization could use it to spread radiation far and wide, using different things. So
right, and you end up with like a generation or two of not so healthy people, because radiation poisoning plus testicles plus radiation equal not a good time.
Right. So
ATF open up. The ATF would not give a fuck about this stuff. It's not their job.
This is more of the Nuclear Regulatory Commission. So,
or the FBI, CIA, DHS.
I thought this was interesting, and maybe there are several of these. This guy's kind of hard to watch because he's hella boring, but I kind of like the old guys that have a lot to say about certain things.
Make sure you swap presentation.
Shit. So we'll go through it and, definitely provide commentary, but this is from the National Nuclear Museum, or the National Regulatory Museum. So it's interesting. Don't need an NFA stamp.
Stupid tax stamp. Go screw yourself.
Minority then. I'll try to keep that in mind. Here's one of the things I just went to get. I happened to be there when I was getting some other things. I'm a collector. I'm a horribly addicted collector.
Me too.
Used to be eBay.
Me too.
But eBay doesn't have as many radioactive and cool things as they used to. They've
really taken a lot of them away.
You got to go on Craigslist for that. I mean, don't go at all.
Craigslist Middle East.
Craigslist Chicago.
A lot of nuclear weapons, as you know, have been disassembled. And a lot of that work has occurred in New Mexico. And I have scarfed up weapons. Well, weapons parts. I guess I don't have a whole weapon. And I'll show you someone, but that's supposed to be one. And if anybody
you could, if you tried harder.
Technology can say, yes, Jay, that's right, or that's wrong. I'd love to know.
That bookshelf has never been used.
I'm a little gullible. I want it to be true, so I acquired it.
It's too nice.
You have somebody who might know. I imagine this was sort of the ignition wires for the implosion device, which we'll talk a little bit. You guys probably know all about those already? No. It could be.
Certainly of the quality.
Awesome.
Quality.
MC number.
Okay, so we're going to pause that real quick. So even the nuclear history, the Museum of Nuclear History, only has two demonstration programs for their nuclear bombs, even though we just obviously saw there's 3, and I fucked up. So this is the Fat Man. That's their wonderful animation. And here is their gun type, or the second type. So, pew, pew. So even the good guys fuck that up, because there's really only 2, I swear.
Well, okay, there is a mix between the 2, which is the thermonuclear one.
Yeah, but it was such an interim step. It really wasn't.
It did not exist. We did not ever actually employ it. It was never actually useful.
Right. I consider it much more to be an interim step or a developmental step than I do an actual bomb.
We only
So,
have two: the one we dropped in Hiroshima and the one we dropped in Nagasaki.
Yep.
Those were test subjects for each, frankly.
Yeah. Yep. For sure.
Stupidly to say, but
And killed a lot of people.
way too many. And then we got, cat girls out of it, so I don't know how truly bad it was, but it was still bad.
Well, you did get anime too.
I love anime.
I know. It's the one thing I don't love about you, Bray.
It's okay. I hate myself for it too.
Well, as long as you know.
I'm self-aware.
That's good. Okay, so we're not so sure on this one, but it's plausible. Okay, guys, energy. Let's talk first about chemical reactions and then about nuclear reactions. There are some fascinating and fun differences. This is a hydrogen molecule. Two hydrogen atoms stuck together with a bond. This is an oxygen molecule, or maybe it's two red balls with springs between them or whatever. But at any rate,
I used to play with those.
hydrogen and oxygen, you can burn them and you can make water. And when you do that, it's an
Oh, the
exothermic
sets?
reaction. It gets
Oh yeah, I want
really
one
hot.
so bad.
It's also what we call a chain reaction. Now,
You can find balls sometime.
They're pretty cheap,
when you burn
actually.
things, they get hot. If you're going to burn these two components and end up with this, what you have to do first is bust
Did you
these
see my
apart.
message?
It's just like Tinker Toy. You got to pull them apart and then reassemble them. That's why you need a high temperature to get things going. The way you normally break these things apart is to make the mixture hot enough that the speeds of these things, when the temperature's higher, molecules move faster.
Okay.
Speeds of these things are enough that they whack into each other and break each other apart. That's why there's such things as ignition temperatures. We have to disassemble before we reassemble. Once you've got them busted apart, then these pieces are going to come back together again. And the key for the whole reaction being exothermic, a reaction which creates heat, therefore can create pressure, therefore be used to make ordinary chemical bombs, is that when the parts are pulled back together in this new molecule, as opposed to the old molecules, the force with which they're pulled in is much stronger than the force that they were held together.
Isabella, if you've ever seen a college campus, you can definitely do some damage in a school microwave.
This ball gets pulled in at the last moment. It's got way more speed than it needs. It's shaking, and that means it's hot, and it shares that energy with the neighbors, and everything's moving fast, which means everything's hot. So the reassembly pulls these things really hard, and that's why it gets hot, because speed is temperature in the case of chemical reactions.
Correct. Speed is temperature.
It's a chain reaction.
I like this guy's
because I didn't bring any
answer
matches,
for that.
I actually set off the fire alarm at our school by mistake. And it wasn't even with a fire. I mean, I should have set it off with a fire. I had a fire extinguisher, and one of the things I like to do is shoot off carbon dioxide fire extinguishers because it makes carbon dioxide snow. You guys probably don't do that. Maybe some of you do that. And so I picked up an extinguisher that I thought was a carbon dioxide extinguisher. It was one of those yellow powder things. And I was aiming it at the ceiling right where the smoke detector is. And everybody had to leave their classrooms for an hour. It was very embarrassing. So here, fire, combustion is a chain reaction. If I were to take a match like I do in my classroom and take a piece of paper and light it down here, the reason I have to light it to get it started, I need that high temperature to get the molecules shaking, to bust them apart so they can reform in that tighter configuration. So I light it here, and I hold the paper, and it burns, and it burns, and it burns, and it burns, and it'll burn all the way through. Well, how did it get to burn here if I only ignited it here? What we need over here to get it started is the same thing we needed here. We needed high temperature, lots of thermal energy, but that's provided by the burning of the paper next door. I get this hot,
So this is what I was talking about earlier with the volcano, where you get out of it and you end up with more energy as you started with. You are causing the burning further on. Yeah.
Fires produce it.
Same idea. You start early, you get double the amount of energy, you can light off two. You can light two pieces of paper.
In the case of, these are my notes. In the case of a nuclear fission reaction, we're only going to talk about the bombs that were worked on in Los Alamos. It has nothing to do with the electrons, only to do with the nucleus. That what the electrons are doing and their energy is utterly negligible. For these guys, the electrons have everything to do with what they're doing. We haven't talked about them, but they are everything to do with chemistry. Their rearrangement is what results in the reaction being exothermic. Nuclear reaction has absolutely nothing to do with that. there are fissionable nuclei. Uranium-235 and plutonium-239 are the two materials that Los Alamos worked on during the war. And you can, I hate these graphics, and I don't know if this is even going to show. But, we got a big nucleus here. One of the things I hate in school materials, this one probably doesn't commit the crime, but if they show a carbon-14 nucleus, they'll show 14 protons and neutrons total on one side of a solid sphere. I don't know what's in the middle and on the other side, but they'll show 14 little balls on the side you can see. That's dumb. Do we need this thing? Help me out here, guys. So this one may be okay, and the key with nuclear reactions, the nuclear reaction is the splitting of a nucleus in terms of what Los Alamos did. Okay. Yeah, right. I'll try. Do you guys use these things when you're in your classes? It's foreign technology to me. Okay, all right. The overall game is we want to make this guy fall apart into two pieces. And the way
These are the
reaction started typically is with a little neutron.
daughter molecules that we were talking about.
Here as we move along. But for certain nuclei, uranium-235,
I think I was far more interesting than this guy, but it's always good to rely on the ancients to teach us fission.
This guy has a more in-depth intellectual way of describing what we were putting in the layman's terms.
And then some more neutrons
Right.
are created. Now, what I hate about diagrams like these,
As long as I can draw those connections back, I feel okay.
If you really have a neutron come along in your nucleus, the reason why these guys then move away from each other, once the nucleus gets started in two pieces, now, even those of you who aren't upper school science teachers, the nucleus has got protons and neutrons in it. The protons are positively charged, the neutrons are neutral. So we
See, I hate when they do that shit, though. When academics say, for those of you who aren't assholes like me.
True. I hate that.
I'm not a fan of that. I'd rather explain it in ways people could understand.
If that's what's going to happen.
So that was the first, and we're not going to watch more than one, but so that was the first episode of that. It is on their website if you want to take in any more, but I think we did a decent job explaining it. There's one more thing that I wanted to bring to our attention. So uranium enrichment begins at Southern Ohio facility.
Oh, yes. Oh, yes. Y'all ready? We're starting, boys.
So I'd like two things to be perfectly clear. This is a joke, and Brian and I are very close to Ohio.
Super close.
Very close. Like, I could pick his ass up. We could drive to Piketon, Ohio. I could drop him off and still make it home by dinner.
I passed through Ohio to get to this man's house. Also, Shenny could and should. 100%. Just link mighty and happy days for all.
Wait, what?
Sniped for a bit. Wasn't sure if you should or could.
Absolutely.
Should and
welcome
could.
to anytime. Yeah.
Link this guy. Get more subs for him. He's pretty damn close to 1.75 thousand.
I know. Don't tell Jessica Reloaded, but my goal in life right now is to pass Jessica Reloaded, and I'm getting fucking close.
You're getting damn close, and you should be.
Real close. She's got 1.66. I have 1.58. So, I'm close.
YouTube
close.
wouldn't care at all, and if they try to fight it, then... Oh, geez. I don't know what we should do after
that. So... Is it in the headline? Because I didn't actually watch it.
I didn't actually watch the video because every time I watch Fox's videos, I get a headache because the ads are so loud.
Jesus. All right. Fuck that. I'll just read. I got the storage silo. You're actually in Texas. They actually have some facilities down there that I'd like to visit. Uranium enrichment is getting underway this week at a facility in Southern Ohio. A federally authorized demonstration project considered critical to produce the type of fuel needed for newer, more efficient nuclear reactors and weapons.
Mostly probably weapons.
Yep.
We want to probably end up surpassing Russia because they have approximately an extra 200 or 300 warheads on us. Whether or not they work is another story.
With their current withdrawal from SALT and the fact that we're still abiding by it, they've actually surpassed close to 500 more than us at this point.
Oh, really? Shoot. I was looking at old numbers, and I guess.
Yeah, since the Ukraine war, Russia's withdrew from START and SALT, and we continue to abide by it. So.
Oh, God.
Yeah. So, South SC nuclear plant issued a warning over another cracked emergency fuel pipe, latest in series of issues. Great. That was a different story, but Bethesda, Maryland-based Centrus Energy Corp will be producing the high-assay, low-enriched uranium at the American Centrifuge Plant Piketon, about 68 miles south of Columbus. That form of uranium contains far more of the isotope U-235 than is typically found in current nuclear reactor fuel.
This is the halfway point between nuclear fuel and weapons-grade fuel.
Right. So we saw that fuel should be enriched to about 1.5%. If it's typically more than found in current nuclear fuel, we're probably pushing that 2%. And traditional weapons grade fuel, as we learned tonight, is between 3 and 5%. So we're getting a little bit, yeah. I mean, I guess you could say about halfway there, which is something that we could easily surpass. So.
Yeah, just refine a little bit more, you're good type of thing. I mean,
right. Just leave it cooking.
There, living on a prayer, you know?
Yeah. An event on Wednesday, Centrus Chief Executive and President Daniel Poneman called it the first launch of U.S. technology uranium enrichment plant to begin production in this country since 1954. I wonder why we're doing that. I wonder why.
Well, we actually did. As soon as Trump got into office, we slowed production of weapons grade uranium by over like 50%. I think we were only producing about 25 to 20% of what we did before.
Right. And
so we're ramping up production again because we have warmongers in power.
Well, that's true. We also sold a lot due to the Clintons to Uranium One, which sold a lot of our fuel to Russia, too, as well.
Yeah.
As our
you wonder why we have less than them in terms of bombs.
Right. He said it will fuel smaller and more efficient nuclear reactors, so we'll have longer operating cycles as well as fuel for existing reactors.
Very true.
X to doubt. Because they'll find that pushing it that extra 1 to 3% will be so much more profitable for them. So of course they're going to do it.
They're going to slow down reactions in those reactors, increase the coverage of the fuel rods, and they're going to get so much more with less burn.
Yep. So the 3,800 acre site was where uranium had been enriched until 2001 at Portsmouth Gaseous Diffusion Plant. Poneman said the U.S. has become the world's largest importer of enriched uranium. Cleanup and decontamination of the Portsmouth plant are continuing. So they're building a plant where one used to sit. So
it was probably decrepit, which is probably a good idea for them to tear it down and rebuild it because we have new technology anyway.
Right.
But
right.
If they need to remake new power plants, that's probably a good idea.
Yeah, for sure. Centrus is now 125 workers there, but hundreds more may be added.
90% are welders. Sorry.
Are they really?
Oh, probably. The amount of welders that are in nuclear power plants is really high, and they're all paid really, really well.
Well, yeah, because they're working with pretty dangerous materials. And in fact, I mean, a nuclear reactor isn't that fucking crazy if we're here.
Sure, but bad welding will fuck it up really bad.
Oh, yeah.
But it's a lot of concrete layers and welders. Those are a lot of the people who are made for nuclear power plants.
So we'll watch this video real quick, and then, because then we'll be right at 2 hours, which is where I like to end it.
I thought you were
so
going
this
to
is,
say the N word. Shit.
I mean, if you want, you're black, you can say it.
Nope.
So, so this is thank you top 5 for the footage. I know you're gonna strike me, you bitches. I'll just mute it after, so if you're not here, you won't see it later.
If it's music, just mute it.
Starting a nuclear reactor.
No, they like the footage. So this is what a nuclear reactor looks like when
So
you
if you look
start
at,
it.
there's a lot of surface area on those fuel rods, which is the important portion. Surface area is super important because that's where heat transfer occurs.
Right. So
The
that's
taller a reactor, the better it is.
Yep. So that's that zirconium fuel rod that I showed it a couple times in the stream. So those are those in the middle right there. They're just longer.
Yeah, and after you get to about about a half a foot into the water, that's just there to keep it from over boiling, because all the radiation is collected within like the first 3 inches of water or so.
Yeah. Water is a magnificent shielding mechanism. So I like to hear it. There.
Oh, that was fucking awesome sounding. Sweet. Did you hear that? Oh my god. So what's that little gun thing on the side there? Do you know?
Oh shit, sorry. I pushed it. So that little gun is basically a camera, a high-speed camera to see how everything's reacting.
So that was a high-speed camera? Awesome.
Probably has some thermal capabilities as well. Just to see, but definitely
you can
a camera.
see radiation via thermal, can't you?
Yes.
Because radiation is essentially heat.
Correct.
So you can definitely see that. Make sure it's not penetrating through the water.
Right. So, if there was any kind of boil off, or if there was any kind of runaway, that's what they would use that for. So you have these huge cores. You have these huge buildings, huge cores.
Aren't the cores underneath it, like the beehive looking shit underneath it? Isn't that the heat? Well, it's not. Aren't those the cores?
In some of the massive reactors, but you have these huge pools, huge cores, and this is your reactor core. You can see again those zirconium tubes.
Yeah, so, the beehive looking shit. Increased surface area is the important part.
Right.
The more surface area, the better.
Right. So these are the size. This is the size that I had in my hand earlier. This is just for scale, from a test reactor. So I still have it in my hand. I just turned off my camera. So.
Slow startup. 6 times speed.
6 times speed, yeah. So it's such a slow.
Yeah, that's a slower start because there's a lot of fuel cores in there.
And this is a test reactor, so this isn't a power producing reactor. So they're irradiating different materials to try and get new compounds and new isotopes. So this one is strictly for the scientific. So that was probably part of the startup, is that they wanted to irradiate very slowly over a certain period of time. Well, I believe this one's at MIT.
I would assume it's all the same stuff inside those tubes. And all the same setup inside those tubes. But I would think that if they were doing another one on the other side, that it would be maybe different stuff. But this one right here is all the same stuff. And I guess it was slow startup, but if it produces what it needs, it's great.
Right. I know MIT, if this is MIT's, they put various different materials separated by graphite. So they'll put a row of... Oh, yeah. It's really weird. So they'll put a row of, I don't know. Let's say we want to make iron, radioactive iron, and they're like, fuck, if we bombard it long enough, maybe it will happen. So they'll put a row of iron, and then they'll put a row of so on and so forth all the way down. So
those sensors would be incredible.
Oh yeah. Yeah. And there's its operating 1 megawatt. You can see
That's
the
gonna
glow.
get bright for people who can't stand bright things. It's gonna get real bright real quick.
Yeah.
If it goes past one megawatt. Nope. Okay.
And you can see the really cool part about this is you can see those control rods. So these are the neutron absorbing control rods, and they're slowly pushing them into the reactor core. So
Graphite
this one's
usually,
cool.
right? You said usually.
Yeah.
Still.
Yeah.
Okay.
Moderators. So. And we know all mods are gay, even Jacob Castro, who's my Rumble mod.
Can we back up maybe about 10 seconds?
Sure.
There was a sound that I think is important to hear. Yeah, right there. That sound, man. That is louder than like 6 gunshots.
Oh yeah.
The amount of energy needed to start this stuff is really high, but keeping it started, it'll keep itself started. It's beautiful.
Right. Well, it's starting the reaction, and then after that, it's self-sustaining. But you have to have enough to break those first particles apart to really make it start bumping and grinding.
Right.
So.
That sound of the gunshots almost sounding kind of sound to me is just that's so much energy going in. That's just what it sounds like.
Yeah. Well, it sounds like if you lose power in that hum where you lose power, and then when your power comes back on because they restored the line in the storm or whatever, that's exactly what it sounds like, but at a higher degree.
Oh yeah. No, my work loses power all the damn time.
Maybe if you guys stop producing meth, then it wouldn't run out of power so often.
Hey, we need meth, dude. It's delicious.
Meth is my favorite. All right, we'll keep going.
Again, those sounds loud.
Yep. I mean, you're talking immense amount of power.
Reminds me of the Iron Man reactor in his chest.
Yeah.
$1 pulse.
Yeah, so you see this static? That's what gets on my camera if I have an open nuclear radioactive source. By my camera, it's wonderful. Makes you feel alive. But
it's kind of hot.
This is
literally and figuratively.
Very hot. But this is much more intense of a, and you can see the grain. Actually, here's some history, and this is accurate. This is not misinformation, YouTube. Fuck off. So do you know how the people, quote unquote, discovered that the United States was making nuclear weapons?
I actually don't. Does that have to do with the static?
It does have to do with static. Eastman Kodak Company was getting static from Oak Ridge, Tennessee in one of their manufacturing plants in the film. And people thought there was something wrong with the film. They were out enormous amounts of money from damaged film. And they, when they took it back to the lab and tried to figure out why their film had all these pieces of, quote, static, it was because they found out they were testing nuclear weapons and testing nuclear processes very close to their production plant.
So,
Eastman Kodak Company.
Shoot, I think I may have lost it because there was a question I was going to ask that I don't quite know the answer to. Get back to me. Get back to me. I'll
Okay.
remember it eventually, I think.
I'll get back to you. I think this is the last one. There might be one more. $1.50 pulse.
I hope you enjoyed.
I'd pay $3 for that pulse. That was a nice pulse.
I paid 4.
Shit, we're not about to get into a bidding war. You just stand down.
Dude, I only have 4, dude. I'm black.
Oh, okay. I'll go $4.25.
Shit. Okay, I'm out.
But yeah, did you remember your question yet?
I don't. I'm sorry. Nope.
No, you're totally fine. I mean, you can always email me or whatever if you think of it later.
Email?
Yeah.
You don't look at your email. You barely look at your Discord.
That's what I meant. You know what the fuck I meant. You can always send me a message on one of the 19 platforms that I'm on, but don't check. Actually, I've been checking Twitter more now. I don't know why, but it's been the convenient platform of the day. Probably because Cheese sends me fucking 9 million things a day on it. That's probably why.
Oh, yeah, absolutely.
Lethbridge. I was looking. Oh, sorry. I often the way my screen had to work for that Bry game. I was completely ignoring Rumble, and I apologize. But Lethbridge, I was looking at thermal imaging equipment today at a gun show. Who asked if you can see radiation with thermals? That's a weird question. I had to pause. Back live now. My co-host and the chemist, Mr. Brian, asked. So.
Yeah, I asked that specifically because, like, you hear in chemistry all the time, radiation is heat, where all energy is heat. It can all be pretty much one for one transferred into it.
Right.
With, various specific losses, various different, heat capacities and whatnot. You're never going to get like a 100% efficient engine, obviously.
Right.
But so that's what I was asking is it generally considered like, can you see it in the heat camera? Well, obviously you probably can. I just don't know how well.
Yeah.
Which it seems pretty well, obviously.
I mean, you have heat radiation, you have thermal radiation, radio waves are radiation, visible spectrum. Actually, the light we take into our eyes is radiation. You have beta particle radiation, infrared radiation, gamma rays, obviously. Ionizing is the dangerous one, or one of the dangerous ones. They also use that on things like X-rays. Black body is obviously in space. Particle radiation is heavily charged particles that can break the skin and cause damage, but they aren't as prevalent. So if you usually keep radiation sources outside of your body, you're a hell of a lot better off. Then you have things like alpha particles, which can be blocked by a very thin sheet. Alpha is the thin sheet, right?
Yes, alpha is very thin sheet. It's once you get to like, UV and like heavy waves, you start getting to stuff that'll penetrate.
Right.
Alpha, gamma, beta, you might start seeing some penetration.
Right. Microwave radiation, of course, electromagnetics. So your electric motors, your cars, your batteries, your power lines in your house have EM radiation. Your cell phone, your computer, ultraviolet, of course, light sources comes from the sun. Radioactivity, that can be decay. That can be a bunch of different things.
I mean, to bring it back to like, to everyone's, daily life, a microwave, like, a microwave in your kitchen, what does microwave radiation? It's tuned to the frequency of water, which boils the water inside of your food, which causes it to like heat up, which is why I was like, so radiation would be heat because, radiation, microwave radiation, heat type of thing. That's how I thought about it in school. So that's what got me there, was because I was like, I heat up TV dinners all the time. They're cheap, they're easy. But the water in there cooks it, calls it a day, because microwaves will vibrate water. and only water. You won't get other things except for metal, which then sparks and causes fire.
Well, and that's I think that's the thing that people forget. So it's not just the vibrating of water, it's the vibrating of water against the material that you're heating that causes friction, which causes heat.
Right.
So the microwave, the heat is an evaporative loss, for lack of a better way of explaining it, of the system. So it's the vibration that's causing the heat, which then heats the food. So you're moving the particles of water, and that's vibrating, blah, blah, blah. So microwaves are fascinating. They're just incredibly high energy particles coming out of so it's basically a step-up transformer, and then it's actually a really old technology. It's anode cathode technology, and sometimes you'll have a radioactive source, thorium, on the cathode, but other than that, it's mainly just high voltage. So,
Kitty, I wouldn't do that personally. I would personally
microwave. Huh? No,
I would not try that person. Yeah, no. Stop the microwave before you open the door.
less bridge. Yeah, but you can only see visible light spectrum and infrared wavelengths with thermals. Yeah, of course. Then you have beta through gamma. Oh, this dude I know. But yeah, so it's obviously not going to show all of it, but there are indications, and they can tune different optical devices to look for certain things. That's the complex answer to a simple question. Ever put a CD in a microwave? No, now I kind of want to. If you put two equal sized grapes, barely touching, you can actually make plasma between the grapes in a microwave on high.
Plasma meaning fire, or plasma meaning plasma?
Plasma meaning pseudoplasma. You'll see a connection from the sugars. So the sugars will transfer and connect in kind of like what's the word I'm looking for? Like if you have salt water and what's the word I'm looking for? You know what I'm saying? You know what I'm talking about. But
Kitty,
so
the reason why you
pseudoplasma.
see little lights is because CDs have ridges, right? Those tiny ridges are able to make little arcs, which that's what you're seeing. You're seeing the tiny arcs in the CD.
Right.
So there are those microwave TV fucking Chef Boyardee cups of chili where they tell you to put the plastic on there and then microwave with metal still attached to it.
Mm-hmm.
You're not going to spark because there is no ridge to ridge connection.
Right.
So what you're seeing in that CD is the ridges arcing to other ridges. And I would say don't do that because fire.
Unless you want to take apart your own microwave and do your own experiments with it, which I do not recommend because
do not
very
try
dangerous.
this at home. It has been said many times over for a reason.
Do not try this at home, even though I've done it at home a couple times because I needed some high voltage transformers and they're cheap.
Me and Meat will do this over at his house. Let the professionals do it.
Exactly. People just chuck fucking microwaves all the time. I don't want the microwave. I just want the fucking transformer in it.
I want the explosion. Thank you.
Yeah. I just want the transformer. And then, you just wrap less windings and blah, blah, blah.
Left Bridge got this. Yeah. Do not try this at home.
That makes it more fun. When there's a disclaimer, which we always have, nothing constitutes advice. I should say don't do anything I would do. I
feel like Minecraft advice is perfectly okay because I know the best Minecraft advice, which is carry a bucket with you.
What about a CD's nuts so I can microwave that? Isabel, you're drunk.
Isabel, show me your nuts. I mean, feet. Show me your feet.
Damn it. Don't start your feet again.
Sorry, brother.
But yeah, so that's how to build a bomb. I wouldn't suggest trying it because before you even got into the process, you would certainly have several federal agencies that would be at your door.
Yeah, knocking, not knocking, more like busting down.
Yeah, they're not gonna knock. They're
knock,
kicking
knock,
the door
open up
in.
The door, it's me.
They're gonna do one of those no knock warrants.
Oh yeah. Ooh.
They can do just about anything they want in terms of national security. They can suspend pretty much every right you have. So
Wait, we have
keep that in mind. Somebody told me you did. I haven't looked recently.
Isabel, you got my Discord.
Is that a threat or a promise or yes?
I hope both. Because my wife sees it, it's a threat. I see it, it's a promise.
Back when burning CDs was a thing, I burned Britney Spears album in the microwave. That's probably the best way to do it.
I feel like that's a good way to wipe a CD.
I wonder if you could put a hard drive in it to destroy it.
Hold on. I actually do have like an old Britney Spears CD I can shove into the microwave, then shove it into a really old cassette player.
Oh my god, you are so gay. Of course you have an old Britney Spears
that was
CD.
that was the first oh, wait, or is it either Britney Spears or was it Hillary Duff?
Fuck?
It was one of those two. Was the first physical medium I ever owned because one of my buddies gave it to me.
Ha! Gay!
Oh,
Maybe.
I got that. Damn it. I was looking for that one. That's the one I was going for.
I like that one a lot.
Teacher asked me how I view lesbian relationships. Apparently 1080p full screen HD wasn't the right answer.
That's a thumbs up and channel. Thumbs up from you. Fuck yeah, let's go. Follow this channel. Follow Mighty Meat. This man's great. I love this guy.
What's up, Lethbridge? Glad to have you, man. But yeah, that's gonna be it for us tonight. We kind of broke it down, gave some visual aids. That's about all you can do, right? So
legally.
Yeah, I mean, until somebody sends me plutonium, then I'm at a loss. I can't do much more.
Until shall not be infringed is truly enforced, and I can have my own nuclear weapon in my backyard.
Right.
This is the best we can do. Sorry,
this is the best we can do.
Gents and gentettes, is that the correct phrase?
Something like that.
Like that.
Hope you learned something. Do not do anything we do on this channel ever at home because it's not a good idea and somebody probably will die. I have a willing sacrifice in Brian, so
don't sacrifice me. I'm not Aztec.
He signed the contract, so
my wife might.
That's all we can do. All right. So yeah, that's gonna be it for us. I hope you guys have an awesome evening. Tomorrow we're gonna do prepping at 2 p.m. Eastern time. With Fast Group, Cool Frog, Mr. Stephen Gosney, and maybe some other people. So we're gonna have a good time tomorrow and talk about some more relevant topics. But that will be it for now for me. Do you have anything to show? Have you looked at games yet?
At the moment, there's not a whole lot. There might be something coming down the pipeline. I'm not going to say shit, but there might be something.
Oh, tease. We won't learn until Friday then, because he's only a weekend lover.
I legitimately work every day, and when I don't work, it's me picking my wife up from work.
That's what they call it now.
Yeah, sadly. Yeah, no, there might be something. I'm looking hard.
Okay, I'm sure you'll find something. Something will come out
definitely.
Soon, but
all right,
look me
up Nuclei Gaming, rumble.com. That's the only place I'm at. You can't find me on YouTube because fuck ScrewTube.
I agree. But it's nice to be over here as well. All right. Thank you, ladies and gentlemen. I will see you guys soon. Take care. Good night.